Hey physics students, here we have another tutorial problem video. This one a little bit more complex, probably take two video clips to get through. So we have here in this problem conservation of energy, work, forces, and kinematics all wrapped up into one. And so for this situation above we have the following information. The 5 kilogram box shown is sliding along a frictionless surface with a velocity of 10 meters per second when it encounters a 5-meter long patch of rough ground followed by a frictionless 40-degree incline that is 4.5 meters long. The mu sub k value for the box and surface is 0.22. And I probably should have been a little bit more clear, but by box and surface, I simply meant this part, the rough part of the surface, not the smooth part. As said in the problem, this part right here is frictionless. So the problem is separated into three parts. We'll first deal with part A. Part A says how much energy is transferred to internal energy by friction. And so we know that change in energy is equal to work, and the work equation is force times distance. I left off the times cosine theta, which was an oversight on my part, but as we can see here, the force of friction will be directed to the left, and the velocity of the box is actually going to the right. And so since those are opposing each other, we're going to wind up with a negative value here for the work done by friction, or the energy transferred by friction. So to find the frictional force, we use the mu sub k value of 0.22, multiply by the normal force, and get negative 10.79 newtons. Then multiplying by the distance over which that force was acting, we get a total of 53.96 joules of work done by friction. And so the negative sign, of course, showing that the work was negative. Now, moving on, I'm not actually going to do part B yet, but we're going to set up the information we need to do part B, which is will the box reach the top of the incline? And if so, what velocity will it have? Well, we need to start doing an energy analysis of our system. So as we know, energy is conserved. So this 1 up here is showing this area. This whole area is what I've labeled as 1. So the energy in this area of the system, 1, is going to be equal to all of the kinetic energy the box has. Once we find that amount of kinetic energy, we know the total amount of energy that will be present in our system. And so to find that, we use the kinetic energy equation of 1/2 mv squared. So we get 1/2 times 5 kilograms times 10 meters per second squared is equal to 250 joules. And so this value, 250 joules, tells us that total in the system we have 250 joules of energy. Now the energy at point 2 is going to have to be equal to the energy at point 1. The situation here is going to have changed. After the box slides over this rough surface, it will have slowed down. So some of the kinetic energy we would expect to be missing. We know exactly how much actually, 53.96 joules. And so some of that energy that became internal energy that will later be radiated away as heat is now going to be taken away from the kinetic energy. So mathematically we can say 250 joules is equal to the kinetic energy, and we're at point 2 now, at point 2, plus the energy dissipated by friction, or the energy transferred to internal energy by friction. And so we find the kinetic energy of the box at point 2 after doing this subtraction as 196.04 joules. Okay, so knowing that we have 196.04 joules of kinetic energy, we can now find the velocity of the block right before it's going to get on the incline, this 40-degree incline. And so to do that, we set kinetic energy again equal to 1/2 mv2 squared, v2 meaning the velocity at point 2. Solving the equation for v, we get square root of 2 times the kinetic energy at point 2 divided by mass, and that comes out to 8.86 meters per second. So the box has lost 1.14 meters per second of velocity after sliding across this area here where we had some friction and the coefficient of 0.22. So the question we're going to answer now is, will the box reach the top of the incline, and if so, what velocity will it have? In order to do that, we first need to know what the velocity is of the block right here at point 2. And that we calculated in the previous part as 8.86 meters per second. So now in order to figure out the acceleration of the block as it travels up this incline, we need to set up a force analysis. And so it's a relatively simple force analysis. We have the normal force of the block, and we have the force of gravity on the block, so going straight down. And so by tilting our axes, a process we're very familiar with, we can separate the force of the earth on the block, 49.05 newtons, into two components. the component on the y-axis and the component parallel to the x-axis. And so on the x-axis, we wind up by doing 49.05 times the sine of 40 degrees is negative 31.53 newtons. Okay, so we have this portion of the force of gravity, the x component, is going to wind up resulting in an acceleration of the block in the negative direction as it travels up the incline. And so now we can figure out that acceleration because we know that acceleration is equal to force divided by mass. The force of friction opposing the current positive velocity of the block will be negative 31.53 newtons. The mass of the block is 5 kilograms. And so we have a negative 6.31 meters per second squared value for our acceleration. So at this point, we know a couple things. We know the initial velocity, we know the acceleration of the block while it's on the ramp, and we know the length of the ramp, remember, is 4.5 meters. So knowing those things, we can use the equation v final squared equals v initial squared plus 2a delta x. The only thing we're missing here is v final. So by simply taking the square root of both sides and plugging in numbers that we found previously, we can find that the box does in fact reach the top of the incline, and when it does so, it'll still have a velocity of 4.66 meters per second. And that takes care of part B. So now moving on to the final part of the problem, we're asked to make a series of quantitative LOL diagrams using the locations marked 1, 2, and 3 on the diagram above. And so, remember that here we have the first part of this system, the first part of this scenario, part 1, all the energy was kinetic. So the energy at point 1 is equal to the kinetic energy at point 1, which is equal to 1/2 mv1 squared, and that got us 250 joules. Then at point 2, recall as we did as we set up the problem for part B, we're going to have lost some energy, lost some kinetic energy because of friction, and so now we're going to wind up having 196.25 joules of kinetic energy left over and 53.96 joules of internal energy, which was the result of the frictional force acting as the box slid across that rough surface. And that work was done right here. This again also was done in a similar fashion on the second page, in the second part of the problem. And what we haven't looked at yet is energy analysis at point 3. So at point 3, the box is at the top now of the incline. And so keeping in mind that our system is the box, the earth, and the surface, we know now that the velocity of the block at the very top of the incline was 4.66 meters per second. And so we can find the kinetic energy of the block at point 3 using that number here for velocity 3, 54.29 joules. We know the height of the block by doing some trigonometry here. We have a 4.5 meter long hypotenuse at a 40-degree angle, which is a change in elevation of 2.89 meters. Tells us that we've lost some more kinetic energy to gravitational energy by using the gravitational energy equals mgh. We find that's 141.88 joules. And since there's no more friction, there is still energy internally due to the friction of the system back at point, or as we traveled across the rough surface, of 53.9 joules. And when you add up all of these numbers, you get back 250 joules, which proves to us that energy was conserved. Hopefully this has been helpful, and good luck on future problems.